Okay, I thought I'd quickly chuck up a video about separation of variables for our first day of remote learning. I think we're up to number 5. Um, so what we're looking at here is solving differential equations when I have both an x and a y in my expression. So it's actually quite easy to do when we manage to completely separate our x parts and our y parts. So what we're trying to do in these problems is we want to create one function that only has x in it and have that function being multiplied by a second function with only y in it. And when we do that, what we can do is we can move all of the y terms to the left hand side of the equal sign, all of the x terms to the right hand side of the equal sign, and anti-differentiate the two expressions independently. So let's have a look at this first example, and we want to solve the differential equation dy dx plus y equals 6x squared y. And we also have an initial condition which is going to come into the expression to find out what c is. Okay, so as mentioned, we want to set this up so we have a function in terms of x multiplied by a function in terms of y on the right hand side of the equal sign. So in this problem, what that looks like is my first step is to get the x's and the y's all on the right hand side so I can try and set up my two expressions. Now at the moment, this part of the function has got x and y jumbled up, so I haven't separated my variables. I haven't got x separate from y. So what I'm going to do in this particular case is I'm going to take out a common factor of y. And when I do that, I can see what I have now created is I have separated my y terms, and my y terms are being multiplied by the x terms. So this is my g of y, this is my f of x. I've got my two expressions. Okay, so next step, I'm going to divide by y on the left hand side. So I'm going to bring all of my y bits to the left hand side and make it 1 over those y parts. And on the right hand side, I'm just going to leave my f of x part. Okay, so now I've completely separated my variables. I've got my x's on the right hand side, I've got my y's on my right hand side. I can now go about solving the differential equation. So to do that, when we're solving equations, we can do whatever we want as long as we do the same thing to both sides of the equal sign. So on the left hand side, I am going to find the integral with respect to x, and on the right hand side, I'm going to find the integral with respect to x. So they both have a dx in it. But what's really handy in this case is that my divide by dx and times by dx, now remember technically they're not divide and times, but for the sake of specialist maths we can always treat them that way, they're going to cancel out. And my expression now is just find out the integral of 1 on y dy on the left hand side, and find out the integral of 6x squared minus 1 dx on the right hand side. So this one's a log, and this one is 3x, no it's not, would be 2x cubed minus x. Now when we anti-differentiate we always get a plus c, so I could put a plus c on the left hand side and a plus c, let's call this one c1 and call this one c2 on the right hand side. But in reality, if we're adding constants, we don't need to add a constant to both sides. Let's just stick it in there once, and that takes care of my constant of integration in one step. So we're going to put just a plus c, and I usually stick it with my x value. Finally, let's find out what c is by using my initial condition, y of 0 equals 1. So we want log e of 1 equals 2x cubed minus on x. I don't want x's though, do I? Because I know my x values are going to be 0 minus 0 plus c. And we get log to the base e of 1 is always 0. And we end up with c equals 0 in this case. Okay, a little bit of tidying up of my expression. I get this. And finally, I can take out the e, put it on the other side of the expression. And I just realised I stuck c back in there when I don't need to. And I have a solution for the modulus of y. So remember that modulus sign is saying, well, it could have been a plus or it could have been a minus. So that means we can say y could be plus or it could be minus e to the 2x cubed minus x. And this is where we might need to do a little bit of extra thinking about that initial condition. So if we know that when x equals 0, y equals 1. So if x equals 0, y equals 1. If x equals 0, y equals 1. Let's look at what happens when I substitute those values into this expression. I would have a 0 minus 0, which is equal to e to the 0, which is equal to 1. Now, initially, we said it could be plus or minus 1, but it can't be plus or minus 1 because I have to get an answer of positive 1, not minus 1. So for that reason, we can just exclude this minus sign and just take the positive version. So I'm going to get rid of all of that, get rid of that, and I don't need any of these lines. I can actually just say if x equals 0, y equals 1, therefore y equals e to the power of 2x cubed minus x. And I'm going to get rid of that plus sign. And that's the end. Solved. Let's have a look at another second example. Very similar case, but a little bit different. We've got sine squared here now. And it's been a while since I've done my antiderivatives of sine squared, and I haven't got my formula sheet in front of me. So let's see how I go with this one. I'll have to try and remember my double angle formulas. No doubt I will forget them. In this particular case, I've got y squared on the bottom line. So this is my function g of y already on the bottom line. And this is f of x on the top line. My variables, my functions of x and my function of y are already separated. So in this case, I'm just going to move the whole function g of y to the other side of the equal sign by multiplying and write it as y squared dy dx equals sine squared x. Okay, so now we're going to take the integral in terms of x on both sides, and I could write dy dx times dx, but I'm going to save myself the time. I don't really need to show that step, so I'm just going to write dy and the integral in terms of x on the right hand side. Cool. Left hand side's easy to do. That's a 1/3 y cubed. Left hand side, we need to use the double angle formulas, and I'm going to quickly look up my double angle formulas because, as I said, I never remember them. And I haven't got my notes at home. And I'm sure you have all stuck in your formula sheet what the double angle formulas are. So I am going to use cos 2x is equal to, and we've got a sine squared, so 1 minus 2 sine squared x. I probably should remember that by now. It would do me a bit of justice if I did, because I wouldn't have to look it up every time. But you don't ever have to look it up. You don't ever have to remember it. It's always on the formula sheet. So a little bit of rearranging, and we get a half minus a half cos 2x. Substitute that into my integral. Half minus a half cos 2x dx. We can now anti-differentiate this expression to half x minus, antiderivative of negative cos is a negative sign, and I had a half. I'm going to need to give myself a little bit more space here. I had a half out the front of it originally. I need to do the antiderivative, which is sine, and divide by whatever was in front of x. That's what I tell myself when I'm doing those problems. Plus c. Put all of that together. 1/3 y cubed, 1/2 x minus 1/4 sine 2x plus c. Now we just need to find out the value of c, and we're given again the initial condition when y is equal to 1, x equals 0. So that would give me 1/3 on the left hand side of the expression, and on the right hand side this will equal 0, and sine of 0 is also 0, so I get c equals 1/3. Okay, finish off my expression by putting my c back into my equation, and if you like, you can then tidy all of that up by rearranging. It would be the cube root of 3 on 2x minus 3 on 4 sine 2x plus 1, because 3 times 1/3 is just 1. And that would be my final expression. Okay, final example. Same thing again. I haven't pre-read this, so let's see how much of a mess I can make of it. A tank contains 30 litres of a solution of chemical in water. The concentration of the chemical is reduced by running pure water into the tank at a rate of 1 litre per minute. Let's get that info in. Here's my tank. Chemical solution, originally 30 litres. We're going to put into that tank 1 litre per minute, so that is dl dt, and it is going in as pure water, so there's 0 litres of chemical per litre. Again, we've got this case where we've got litres per litre. Bit annoying, but we just have to deal with that. The difference here is x litres is my chemical, so this is dx dl. Okay, so dx dt, the rate of change of the chemical with respect to time, is going to be the inflow minus the outflow. I've just found the inflow will be 1 times 0 from these two parts here and here. If you're not sure how I got that, what I've done is dx dt for the inflow will be equal to dl dt times dx dl. We're going to do the same for the outflow now. So let's work out our outflow. Coming out is 2 litres per minute, and we don't know how much chemical there is in my tank at this time. So that 2 litres per minute is dl dt, and the rate of change of x with respect to litres will be X litres of chemical. Alright, so X litres of chemical. And in this case, we've got less water going in than what's going out. So the volume starts off as 30 litres, but it is going down by 1 litre every minute. So my outflow is going to be 2 times X over 30 minus T. Tidy that up, gives me dx dt equals a negative 2x over 30 minus t. And by having that inflow equaling a total of 0, we've created this nice separation of variables problem, where my top line is f of x, a function in terms of x. My bottom line is g of t. I've put y there. G of t. Alright, so let's now try and solve this problem. We can find a solution by separating my variables even further. I'm going to bring the 30 minus t to the left-hand side of the equal sign. And I'm going to leave the negative 2x on the right-hand side. I'm going to find the integral of each side. And technically I'm doing the same to both sides by finding the integral with respect to x, but the x is, with respect to x. Oh, does that cause a problem for me here? I think maybe it does. I've just realised that what I've created is not going to work because I've messed up my x and my y integrals. So if I took the integral of this side with respect to x, my x's here and here don't cancel out because they're both on the top line. So that doesn't really work for me. So when I've separated my variables, I've moved the t to the left-hand side. What I actually needed to do is I'm going to, so let's just rewrite that expression again. Dx dt equals negative 2x over 30 minus t. I want to put the expression 2x over with my integral, because in this case, like before, that x is actually the same as what was y in the previous problem. That is like y in my previous problem. That is like x in my previous problem. That is x in my previous problem. I know they're not x and y, they're x and t now. But look at the difference now. If I make this negative 1 over negative 2x dx dt, and on this side I leave it as 1 over 30 minus t. If I find the integral of both sides with respect to t, dt, then in this case we can see now my dt cancels out and I'm just left with x. So I can anti-differentiate the left-hand side with respect to x. I can anti-differentiate the right-hand side with respect to t. And I'm going to do one extra thing here. I've just spotted this. I'm going to move that minus to the other side. So rather than bringing the minus across, I'm going to leave it on the right-hand side. And I hope some of you might have noticed why I did that. Why? Because now on the right-hand side here, the top line is a derivative of the bottom line. So it is a simple log problem. So this one becomes log e 30 minus t plus c, and my right hand side is going to become 1/2 log e of x. Okay, I don't like the modular signs. I'm going to get rid of them if I can. X will always be greater than 0 because there's some chemical in the tank initially. So pouring fresh water in is going to slowly drain that out, but it's never going to be equal to 0. There's always going to be a small, tiny part in it. So if x is greater than 0, I don't need the modular sign on this side. And as well, the value for t, the time that it takes, well, it will also have to be less than 30 as well, because if time is more than 30, there's no water left in the tank. If there's no water left in the tank, we don't have a rate of change problem. So t will be less than 30. So on this side, given that condition, I can ignore the modular sign because what's inside the brackets will always be greater than 0 when t is less than 30. Okay, do we have an initial condition? A tank contains 30 litres of solution of a chemical in the water. The concentration of the chemical is reduced by running pure water. The tank contains X litres of the chemical at time t minutes. Find the fraction of chemical in the tank after 20 minutes. So we want to find out how much is in the tank after 20 minutes. Okay, now we know initially that I'm not actually sure how to do the rest of this question. So I'm going to leave the video there and I'm going to give you a better solution in class when we come back. And I'll have a little bit more of a think rather than keeping this video going for too long. So thank you for watching this far. I will get to you regarding the final part of the problem once I've had a chance to think about it.